Okay, so hello everybody. So today we have an MSc seminar by Ori. So let me briefly introduce Ori. Ori holds a BSc in computer and software engineering from the electrical engineering department from 2019. He has about 3 years experience at the computer vision department at the Rafael, which he did during his BSc studies. He also has a research internship at ABM and is about to start a new internship at Bosch AI research team. And he has been pursuing his master's degree in computer science department since 2019. All right, Ori, go ahead, please.
Thank you. Hi, everyone. My name is Ori Sztyglic, and today I'm going to talk about online POMDP planning via simplification. Many thanks to my advisor, Vadim Mindelman. So all around us, autonomous agents are emerging, whether it is for delivery or surgical procedures. Since such agents interact with the physical world, many autonomous tasks often require to account for inherent uncertainty. This uncertainty can originate from uncharted environment or even noisy measurements of the equipment we have, such as LiDAR. The challenge becomes even more greater when our autonomous platform is required to make online decisions, meaning it has a few seconds at most to decide on the next action to take. Nowadays, such a requirement is widely on demand for various self-navigating transportation solutions. Today, I'm going to start with some background for our work. I'll briefly mention early seminal work and the state-of-the-art solutions for our considered setting or easier settings. Then I'll move on to explain our approach, contribution, and how did we evaluate it. And finally, I'll give some future work possible extensions and leave some time for questions. So background. The mathematical model we assume, not only in this work, but also in our group, is a partially observable Markov decision process, or in short, a POMDP. A POMDP is a tuple containing the state space, action space, observation space, probabilistic transition and observation models, a reward model, and a discount factor. Under this setting, an autonomous decision-making agent pipeline should look something like this diagram on the right. Given the agent internal belief over the state, he plans into the future, and based on the planning session, he picks an action or a sequence of actions, executes the action, acquires an observation from the real world, and finally, using this observation, updates the belief over the state. In this work, we focus on the planning part here in blue. We model the world as a POMDP to account for existing uncertainty. Instead of planning over the agent state, which we do not have access to, the agent maintains a posterior distribution over the state, which is commonly known as the belief. The belief is known to be a sufficient statistics for the history, which given some time step is all the actions taken and observations acquired up to this time. Now, since we don't have access to the state, we instead plan over the probabilistic space in which the belief resides. An important property is that now using the belief, we can account for information theoretic rewards, such as its differential entropy and more. These rewards can be useful when a planning task has no predefined goal. Many examples exist, such as search and rescue missions, mapping of dangerous locations like collapsed caves or underwater wreckage. In the online planning setting, the agent starting from his current state or belief needs to consider multiple future trajectories realizations. In our setting, a single trajectory is defined by a sequence of actions and observations needed to update the belief. A common way to organize such information is a tree or a belief tree, where the root is our current time belief and future belief nodes along the tree are generated using a black box simulator or by having access to the observation and motion models. Since we deal with an online setting, the tree size is usually restricted by some hyperparameters such as maximum tree depth and branching factor, maybe number of iterations, or simply a clock constraint. So what does this tree has to do with planning? Since in our model, each belief node induces a reward, the decision-making or planning goal is to find the action sequence that induces the highest cumulative discounted reward. More formally, we would like to find a policy that maximizes the value or the objective function. It can be calculated by considering different actions and taking an expectation over the observations. This setting raises many challenges. First, building the complete tree is completely intractable. Even if the branching factor is not so big, the number of nodes grows exponentially with the depth of the tree. Obviously, when it is bigger, the problem is much harder. The problem is commonly known as a curse of history, which is illustrated here in this video. Another problem is the curse of dimensionality. Building the tree requires to create new belief nodes. So the number of possible states grows exponentially with the state's dimension, and correspondingly, so does the belief. This can result in great computational burden. Additional challenges exist, such as continuous domains, non-parametric beliefs, a need to account for expensive to calculate information theoretic rewards, and high dimensional settings. In our work, we consider all the challenges, leave out the high dimensional setting. As mentioned, we consider non-parametric distributions. This is a more general setting than assuming the belief is, for example, a Gaussian, which can be useful when it is in fact some sort of multimodal distribution. Typically, in order to approximate an unknown distribution, one needs to perform some sort of sampling. In the problem of planning into the future, commonly state samples and observation samples are generated in order to build the belief tree. Sampling is a vast research field in statistics, information theory, machine learning, and more, and getting any deeper into it is out of the scope of this work. A celebrated method meant to deal with the curse of history and dimensionality is the Monte Carlo research algorithm. Essentially, it is an iterative method that starts by selecting a path down the existing tree, expanding the tree by maximum of one node, update its value by some sort of simulative episode, and finally update the newly discovered information all the way up to the root. It breaks the curse of history by revealing only some sections of the full tree, and it breaks the curse of dimensionality by using a predefined number of state samples. From the description of the algorithm, we can gather the tree is built incrementally using a predefined time frame or iteration budget. I should mention that the algorithm requires for step A some sort of heuristic or exploration strategy to decide its way down the existing tree. A common heuristic is the UCB, which I'll talk about more later. Further, it requires a rollout policy for step C, the simulation part. This can be a simple random action selection policy, but more sophisticated method exists. Related work. So who are the state-of-the-art solvers that can handle our challenging setting or similar to our setting? I remind you that we consider online POMDP planning with continuous state and observation spaces and information theoretic rewards. Two main approaches exist for online POMDP planning, supporting a huge state space, which are POMCP by Silver and Venice from 2010, and Despot by Yi et al. From 2017. POMCP was the first work to use MCTS to solve POMDP in an online setting. Despot's original paper was published around 2013 and introduced an MCTS-like mechanism with additional modifications, such as heuristics for observation selection, regularizations to avoid overfitting, and the use of upper and lower bounds to prune tree branches when possible. However, these two papers are not suitable for continuous observation spaces and information theoretic rewards, since they will suffer from particle depletion, among other things. Throughout the last decade, many researchers introduced many extensions to POMDP. POMDP observation widening and PFT-DPW by Sandberg et al. Were designed to deal with continuous spaces, but only the PFT-DPW is suitable for information theoretic rewards. IPFT by Fisher et al. Builds upon PFT-DPW and uses some asymptotical approximations to guarantee asymptotical approximations guarantees to incorporate differential entropy approximation to this algorithm. Raw POMDP is a recent work that aims to incorporate information rewards to the POMDP algorithm, but it cannot handle continuous observation spaces. Following work to Despot Alpha is suitable to continuous spaces, but it cannot handle information theoretic rewards. Out of the lot above, only these four use particle filter, which lays the basis for continuous domains and information theoretic rewards. But in truth, for various reasons, out of those four, only these two can handle information theoretic rewards in continuous state and observation spaces. If you asked me in what solution can handle with which difficulty, I've summed it all up here in this chart. Importantly, POMDP planning is a widely studied problem, and many other early seminal works or innovating solution exist, such as the one mentioned beneath this chart. However, all of them aren't designed for continuous state spaces or the online planning setting we adhere to in this work. Our contribution can be divided to 5 main items. We introduced a new simplification for the setting of POMDP planning with non-parametric belief representation, considering belief-dependent rewards. Based on this simplification, we introduced novel differential entropy approximation bounds, which are highly functional, as we shall see later. We then show how these simplification bounds can be merged into a general sparse sampling planning scheme, speeding it up significantly. We show how our bounds and essentially every simplification-based converging bounds can be merged into a more specific state-of-the-art MCTS approach for POMDP planning. And finally, for the last item, we provide extensive proofs and an analysis that show our method achieves the same results as a state-of-the-art baseline, but faster. Accurately solving a POMDP is highly intractable. Thus, approximation methods such as MCTS are widely used. You can agree with me that not many works focus on the even more challenging setting we here consider. There are papers such as IPFT or POMDP that add even more approximations on top of the already approximated problem. On the other hand, our work focuses on embedding the notion of simplification to our discussed setting. So, what is simplification? Generally speaking, it is a line of work carried out by the ANPL group that focuses on relaxation of the decision-making problem, while ideally assuring the same solution as the non-relaxed problem. If it is not possible to achieve the same solution with a relaxed problem, the objective error is bounded as a part of this scheme. As I shall present later, we focus on differential entropy approximation when the belief is represented as a set of weighted particles. Just to be clear, this approximation can be achieved via a KDE or a method developed by Bors et al. So we use simplification in order to speed up POMDP planning. Many simplifications exist, and we focus on belief node simplification as seen in the illustration here below. When the belief is represented as a set of weighted particles, we take a subset of particles in order to represent what we denote as a simplified belief. So here you can see in blue the original belief represented as a set of weighted particles, and the simplified belief corresponds to taking some subset of these particles. How can this help us? So instead of calculating expensive information theoretic rewards over the entire belief, we consider a subset of particles and calculate simplification-based bounds over the reward. The reward bounds can be generalized to bounds over the value function. Specifically, we've developed a novel simplification-based bounds over the differential entropy approximation by Bors. So here you can see the first item, the original differential entropy term. The approximation by Bors is here on the second item, and we've developed the bounds here in the third item. In our notations, P of Z given X is the observation model, P of X prime given X and A is the motion model, Wi is the weight of the state sample, Xi, AS is a set of simplified state indexes, not AS is a complement to AS by definition, and const is the max over the motion model, which we have access to since the models are given, as I mentioned before. Our bounds are highly functional with many desired properties. They converge to the actual reward function, which is a differential entropy approximation, monotonically increasing lower bound and monotonically decreasing the upper bound. Bounds tightening can be done on demand. Complexity of O of n times ns instead of O of n squared of the original reward, where n is the number of particles representing the original belief and ns is the number of particles representing the simplified belief. Simplification levels are user-defined, which help us with the incremental tightening scheme. The bounds structure allows a reuse of calculation, moving from one simplification level to another. And finally, worst case time analysis suggests time complexity is equal to the original reward calculation, meaning no time loss whatsoever. As mentioned before, they can be extended into bounds over the objective or the value function. This is possible thanks to the recursive nature of this problem. Planning is all about finding the policy, maximizing the value function, and since we now gather that the bounds can be applied directly on the value function, this can benefit our goal. A very important note here is that our formulation is general, namely the algorithmic planning framework. The simplification-induced bounds over the reward and objective function shown here in this slide are true for any analytical converging to the reward bounds. This makes our approach very appealing, since given such bounds, they can simply be plugged into our algorithmic scheme. Simplified Information Theoretic BSP, or in short, SITH-BSP. So how does this help us with planning? Since the bounds are analytical, we can prune branches when going up the tree leaves to root. In case it wasn't clear, going up leaves to root is the default approach when trying to find the optimal trajectory in a tree. Pruning is done by considering sibling subtrees, upper and lower bounds. Consider here in the slide, the left graph A. We can clearly see that the last policy offers the greatest cumulative reward, but it might have cost us a lot of computational time to discover it. On the other hand, if we had fast to calculate bounds, and the bounds of the best policy were not overlapping with all other bounds, such as seen here in graph C to the right, we could declare the last policy as optimal with respect to all others while saving valuable computational time. Sorry. On the other hand, what can we do when the bounds do overlap? For those of you more familiar with this genre of papers, overlapping bounds is what we have most of the time in Despot HSVI and Lifshitz continuous HSVI, and essentially almost every anytime solver. Fortunately, this is not an issue with our novel bounds, since all we have to do is increment the simplification level, and by doing so, we can tighten the bounds. Importantly, we do so while reusing calculations from previous simplification level. More formally, given a belief tree, our algorithm, Simplified Information Theoretic BSP, or in short, SITH-BSP, it goes leaves to root of the tree and calculates subtree's value function upper and lower bounds. If the bounds do not overlap, we can prune all branches but the best one and keep the recursion up the tree. If they do overlap, we refine the simplification level until we can prune all branches but one. We are promised we can do so since at the maximal finite simplification level, the bounds converge and are just the original reward itself. More details on our paper, Speeding Up POMDP Planning via Simplification, that was submitted to ICRA RAL 2022. While this last paper was rather theoretical, focusing on straightforward incorporation of the bounds into simple POMDP planning scheme, it had some restricting assumptions. Most notable is that the belief tree is given. All the state-of-the-art POMDP planners I've introduced earlier do not build the belief tree in advance, but rather build it incrementally using methods such as MCTS. So our following work, main focus, was to incorporate our approach into a state-of-the-art POMDP planner suitable for our considered setting. The goal, as the last one, was to show a speed up. We chose the PFT-DPW algorithm that I mentioned earlier as a baseline to speed up, since it is the least restricting one. Essentially, it is an MCTS framework augmented with particle filter and double progressive widening. Importantly, this is not a straightforward implementation, and we had to account for many problems. Since the tree is built incrementally in MCTS methods, our main challenge was to assure our approach builds the same belief tree as PFT-DPW. This is quite challenging since PFT-DPW builds the belief tree using the UCB heuristics, which requires direct access to the Q function approximation, which is acquired by summing belief nodes rewards, which we don't have access to anymore. UCB is a technique meant to balance exploration with exploitation, a well-known problem in many fields such as game theory and reinforcement learning. The idea is to choose the action, maximizing the UCB term, where its first element, seen here in the slide, corresponds to exploitation, and its second term corresponds to exploration. The notations here are slightly different than before since we follow the literature notations. Here, H and A are history and action respectively, where the history is a representation for the belief. Q of HA is the belief action value function, also known as the Q function. C is the exploration constant, which is a hyperparameter user defined. N is the belief or belief action node visitation counter. Since it is an iterative method, so we keep track on how many times we've visited in every node in the tree. The solution we chose is upper and lower bound the UCB by replacing the information theoretic associated part of the UCB with our novel bounds. Essentially, we upper and lower bound the UCB, as seen here. This is an overview of the algorithm if you got a little lost. Recall that each MCTS iteration, we iterate down the tree using UCB. Now, since we don't have access to the Q approximation, there can be bounds overlap. When this happens, as seen here in sketch A to the left, we need to tighten the bounds. This is done by selecting some section of the entire problematic area and refine the bounds in it. Selection of the area to refine its bounds is done according to some resimplification strategy of our own creation. After the bounds were tightened, we can continue safely. Our entire algorithmic approach similarly make use of bounds over the subtrees of the belief tree to choose an optimal action. But this time, unlike previous algorithm, we cannot prune branches. The reason for this is related directly to how MCTS works. This was part of the challenge incorporating our method into it. Our algorithm, Simplified Information Theoretic PFT, or in short, SITH-BSP, have three interesting properties. One, the SITH-BSP and PFT-DPW are three consistent algorithms, meaning given the same problem and the same initial belief, the two algorithms will produce the exact same belief tree. 2, the SITH-BSP provides the same solution as PFT-DPW, meaning they will output the same action for the agent to execute at the end of the planning session. And finally, the specific resimplification strategy is a converging and finite time resimplification strategy, meaning our algorithm based on the resimplification strategy is promised to yield the same solution as the baseline after a finite time. All the proof for these theorems, along with the algorithmic scheme, can be found in our paper, Simplified Belief-Dependent Reward MCTS Planning with Guaranteed Tree Consistency, that was submitted to NIPS 2021. Evaluation. Our first work evaluation has two parts. We first study our bounds behavior compared to the original approximation by both, and we compare them to other approximations as well. Additionally, in our setting, we can also compare the ground truth to the ground truth differential entropy. We have access to the ground truth entropy since we define the belief to be a Gaussian and the motion and observation models to be linear models with Gaussian noise as well. This information is obviously not available to the agent, and it maintains and the agent maintains the belief as a set of weighted particles according to our work focus. We experiment with a continuous 2D light-dark problem, which means the agent starts with some initial belief over its 2D location. The agent is given a predefined action sequence, and along the way, it comes near light beacons that lower its uncertainty, leading to a more concentrated belief. We experiment with changing number of particles. This is a passive setting that I just described, which means planning takes no place, since we are interested to see only how the bounds behave. Light beacons are bright light and particles are in yellow. Particles with bigger weight have hotter colors. As you can see, the agent comes across two beacons on the way, one in the halfway and one in the end. Thus, we expect the entropy to decrease twice. The graphs show entropy ground truth approximations and our bounds using increasing simplification levels left to right. Dashed line are the upper and lower bounds, and in orange is the original approximation which they are based on. In blue, we have the ground truth entropy, and in green, we have the KD approximation, which is used by IPFT. The red line is a naive approximation to the entropy that was achieved by assuming discrete entropy approximation to the differential entropy. Here, we see results acquired by using 200 particles, and the graph left to right are using simplification levels 0.1, 0.5, and 0.9, which means simplified belief is represented by 10, 50, and 90% of particles out of the original belief. So for example, here, 0.5, when we have 200 particles, correspond to 100 particles, 50% for representing the simplified belief. Note how when simplification level rises left to right, the bounds are converging. As mentioned, we experiment with various number of particles. Here, you can see results for 100, 50, and 20 particles top down. Please see the original paper for better resolution for all the graphs. To evaluate our approach as a planning scheme, we again use the continuous 2D light-dark problem, but this time, the agent is given the ability to plan into the future. Our baseline is a sparse sampling scheme, which means the tree is built using some parametric depth and branching factor, meaning it is given when trying to decide on the optimal action. The reward function is a multi-objective one, distance to goal, and differential entropy approximation. We consider two settings, 1 and 2. Setting 1 is much easier, and setting 2 is harder. We do so in order to show how the simplification scheme can save more time when the scenario is easier, meaning we demonstrate how adaptive and dynamic our approach can be. We experiment with different structure trees to show our approach works well on all of them. This is the mentioned setting 2. This time, the action space are the four directions perpendicular to the main axis. This setting creates a symmetry problem, which makes planning harder since nodes across the tree often have similar reward values, which result in more overlapping bounds, which leads to more bounds refinement iterations, meaning less computation time saved. Although setting 2 is harder, in this table, we can see our approach leads to significant speedup in all the scenarios we tested. We experiment with changing tree structures, changing horizon, depending on the tree structure, and changing number of particles. We report the mean planning time throughout the scenario for the baseline and for our approach. Just a second. In each cell, the left number is the time it took to decide on the optimal action at the tree root using the original reward calculation. The right number in each entry of the table in bold font is the time it took to our approach to decide on the same action. As we can see, our approach, the right number, while providing the exact same optimal action as the baseline, is significantly faster, leading to a factor of 4 speedup in some cases. The colored plots are a simplification level histogram. It gives a glimpse into the tree and show how, for one of the scenarios, what are the simplification levels in both settings. On the left, we have the harder setting 2, and on the right, the easier setting 1. Note how simplification levels in setting 1 are generally lower, which means the algorithm should save more time as it is really seen in the table. For our second paper, SITH-BSP, we used a similar scenario, but a different baseline. Since we extended PFT-DPW, it is obviously our baseline. We coupled him with the Boras entropy approximation, and the desired result was same planning action sequences, but while showing speed up compared to the PFT-DPW. We also show some high-level comparison to IPFT, which also extend PFT-DPW to information reward, but in a completely different manner. Our scenario, again, is a challenging continuous 2D light-dark problem. As you can see here, our approach to the left outputs the exact same actions and behavior as the PFT-DPW baseline on the middle, but with speed up. On the other hand, since IPFT to the right uses some asymptotical approximations to calculate the information reward, it can perform in a suboptimal manner compared to PFT-DPW baseline, which is built upon. For more details on the IPFT, see the original paper and our related work section. Again, the results show our approach is faster in all of the experiments done compared to the baseline. So for the setting of a POMDP with belief-dependent rewards, we introduced novel highly functional bounds over differential entropy approximation based on weighted particles. We developed a general sparse sampling adaptation to such simplification-based converging bounds, leading to substantial speedup. And finally, developed a general MCTS adaptation to such simplification-based converging bounds, leading to speedup. Future possible work: incorporation of the bounds into other POMDP planning algorithms, incorporation of the bounds into other domains, such as SLAM. Given other analytical converging bounds, they can be incorporated into our existing sparse sampling and MCTS adaptations, and uses of the bounds or some linear variant of them as an exploration heuristics for the rollout estimators required by MCTS algorithms. Many thanks for your time. I'll be answering any questions.
Thanks, Ori. We have plenty of time for questions. Go ahead, please, if anyone has a question. No questions? Last chance.
I guess it was all very clear.
Hope. Okay, so in case there are no questions, let's thank Ori again. Thanks. And thank you all for attending the seminar. Thanks and goodbye. Thanks.
Thank you very much.